Hello. I just so I'll probably wait before I start. Yeah, sorry about the fan issue. Right, so yes, hello and welcome to the first webinar of our webinar series, where we'll be starting off with conducting one webinar each week, and we'll be covering one simulation topic. And this week's topic is called the heat diffusion simulation, where it will be presented by Christy Ashwin. The webinar outline is as follows, where we will get to see diffusion from two different perspectives, the theoretical and the practical perspective. We take a look into meshing and how the various boundary conditions are applied from the theoretical as well as the practical point. We'll also have an insight of the Laplace equation and its function. Then I will take you through a brief introduction of the platform and how it can be used to simulate. And we will take up the simulation case of a mold assembly using the online simulation tool. And we will also post-process the simulation online, and we will conclude with this webinar. So the speaker for today is myself, Christy Ashwin. I'm a co-founder of Caspen Technologies with a master's degree from MIT Manipal in computer-aided mechanical design and analysis. So moving on, we will first look at the diffusion from a theoretical sense. So diffusion, it's a phenomena that occurs only when you see a gradient where there you have a higher concentration of a particular quantity at one point and you have a lower concentration elsewhere. And only when there is a gradient like this that exists will you find diffusion occurring. Diffusion of the concentration of any quantity. It could either be temperature, or it could be any particle, or it could also be electromagnetic. So in this case, we will focus only on the thermal aspect of it. So when you look at temperature, it depends on two factors. One is how much the gradient is, and the next is what is the intervening medium between these 2 points. So it depends on the gradient as well as the property of the intervening medium. So if we take diffusion of a material inside a material, it is basically diffusion process. So diffusion typically follows the second law of thermodynamics, where if you have a higher concentration, it will tend to getting more chaotic and releasing its doing a diffusion study of one dimension in the general sense follows the second law, where the entropy of the system, that if you have a occur in such a way that it gains is either moving from one. Now that you've understood the physical sense of it, material which you're heating consists of so once you start, the case is heat, and thus the practical sense, because they're convective. Now, if you actually connect the two between the hypothetical, we all have diffusion studies under steady state where the temperature difference, you need to understand that it's not the temperature which is delta difference. So upon the spatial distribution of the temperature does not change. It only reaches up to a certain extent of heat diffusion. So beyond that, heat. So another case is the amount of heat at any concentration, the amount of heat entering equal to the amount of heat leaving the section. But if you look at reality, the diffusion process is only one part of it. That of heat transfer, conduction. I would include advection if you're considering fluid flow over the temperature domain. And in reality, you actually have transient talking only about where you have the delta T changing. So hence temperature of the object changes as a function of time. So I wanted to ask the viewers a question, which you can keep in mind, and we'll get back to the answer. So I have a tetrahedral mesh of a simple rectangular block, and you have a hexahedral mesh. Now the question here is, which mesh would yield better results in thermal analysis and why? So this is particularly for thermal analysis and not for structural analysis. So keep in mind, we will get back to the answer of this at the end. Understood diffusion from the theoretical and practical sense. Let's go straight into the problem. The diffusion process and how simulation of that can be done. Taking this case of a mold which has an inlet patch which is set at 900 Kelvin and an outlet patch that is set at 350. So this is the mold where I have broken it down into 3 patches. Patch 1 would be the connecting tube as well as the mold. Patch 2 will be the inlet, which I've considered to be a single block as patch 2. Patch 3 will be the riser, so where the excessive molten metal comes out. So the study of a simple steady heat only when introduced into patch 2, and we will see how the temperature or the thermal diffusion will occur along patch 1. At lesser temperature, put it to patch 3 and also see how the diffusion happens in this region. So the material fluid which we'll be introducing into the mold for study, where I have considered the following material properties. So the thermal conductivity of the material is 13 watt per meter per Kelvin. The material would be 2.70 gram per centimeter with a coefficient of 921. So you have to first be very careful about that we don't have any problems in mixing up different units. So we'll have to convert this density of 2.70 into kg per meter cube. So 1000, where the gram gets converted to meter cube, that is 10 power minus 6 in the denominator. So when that goes up, it becomes 10 power plus 3. Hence, you have to multiply this figure by 1000. Simulate this case. Before we move to the boundary conditions, I would want to introduce the simulation learning platform, where you first have 3 sections. You have and another pane beside that, where you introduce the input parameters for each of these fields. And towards the right, you have 3 tabs: the instructions, the solver output, and the visual output. So first, we will have to one is we have format platform for the simulation. So what I will quickly do is move to take my case. So I have the UNV file. So after you've uploaded or selected the file, you'll have to add the geometry to the platform. So this file will already have the mesh data, and in the next webinars, I will be showing you how these files can be created into UNV and uploaded for a simulation. So the process of simulation is very simple in this platform. After you have completed uploading, you will get a geometry file uploaded status, and then we will move on to defining the time. So let's go back, and I have set 4 important inputs for the time control, which is the start time, the end time, the delta t, and the right interval. So the start time is, we should understand that this is not the is the calculation time, or it's also called as time marching. So what basically happens in these time controls is you try to define what is the time or what is the difference in the time from one iteration to the next. And this is not the physical time in seconds, which I am, because it's a steady state condition, you will not be calculating the change in temperature over time, because that will be a constant. So the end step and the step would be starting from 0, 0.1, 0.2, 0.3 until it reaches 20. And I will be writing these values in for the post-processing at every first second of the simulation time. So we will quickly input these values. So we keep the start time as 0. We keep the end time as 20. We will leave it, and I will want to write my results every 1 second. So after this has been inputted, we shall click on update, and we will complete updating the time controls. I will is basically each term in your equation, what various schemes you would be using. So to further explain what Laplace equation, where you're basically converting equation into a set of ordinary differential equations. So this is the simplified form which we would of the equation which we'll be calculating from. The first being the time step derivative. The next is the diffusion term. Now, if you notice, you have of t, and if you take the coefficient of conduction, that is dt, you will get a Laplacian operation. So I do not want to get into how this operation was done. You can refer standard textbooks for that. In textbooks where Q will be equal to alpha times any cases T by. So what this does is it breaks in your model, and after all the calculations have been volume V, and the volume dt nabla t, and this will be used. We will be getting rid of the ds and using a summation operator across the field f. We will be calculating delta t, and this sf will be found along with delta tf with this temperature at the existing cell or the cell of interest. So this delta t is what we will be calculating across the entire domain between one cell to the next. And this mod d is what the distance will be between those two cells. So I will be explaining you through the scheme. We will leave the, as I showed in the equation earlier, under the we will be specifying the property which you will be calculating the flux for, which in this case is the temperature. T, so will be set at linear in this case. No convective, the divergence which will be set with oil equation. Any of these values, they will already be preset. You specified what schemes you will differentially kind of solvers to find out what your unknown values are in those ODEs. Be using a set of different solvers, which in this case is the simple solver. And the simple is nothing, an acronym for semi-implicit method for pressure linking of equations. En non-orthogonal characters to 2. So this will basically, it's this case being the temperature. So after setting this, the update notification to come up. It's been updated. And we will be using the PCG, or the pre-conjugate gradient. And we will be using preconditioner, which is DIC. We will relative tolerance to 0, and I will give it a tolerance of. So basically, the tolerance is an indication for you to know whether between two iterative residuals is falling within this value or out. If it is falling within, shows that your solution. If it isn't, that means you may have to increase the time duration, and check if you're achieving convergence, or you may have to change some other parameters to stabilize your convergence criteria. So after this is set, so we've just simply put a temperature into solver. And the next important thing is the transport properties, where we will be changing this value, because this again is the dt, which I had shown earlier, that is over here. So we'll go back and see what for which we will calculate the value for dt. Thermal conductivity divided by the, and then get this, divide the result with, you should effectively get this value. Understand that the units for your coefficients you'll have to be careful with. This is meters squared per second. So one the initial condition, that is T, but we will be using two types of boundary conditions. Before I continue further, So I will initial value and the boundary value problem. So we've already finished the initial value. So we will keep we will set the boundary value conditions now, where we have two kinds of inputs. One is to input a fixed temperature at patch 1 and patch 2 and patch 3 is going to have a condition where we'll be setting the absolute at the boundary, which is the adiabatic or the zero gradient boundary condition. A condition. So boundary state, this boundary conditions. There's 4 walls. Will be of xy will be 0. As I said that this is conserved and there is no change in temperature. The total delta T will be 0. It will be contained within this section. And if there is a delta T value, that means there is heat getting lost, and that heat is some form of work. So as T delta T is equal to across the boundaries x lying between 0 to 1 and y lying between 0 to 2. Now we'll check out the boundary conditions. So dou T by dou y at x for all values of x and bottom wall value, since it is a insulated going to be 0. Let's look at T of x, T of given a value wall, which you've given a value of 0. Now for y lying between 0 to 2, that's all values of giving temperature T, giving a by dou 1, that is x for all values of y, which is given a value of, this is supposed to be 0. I've written it as 200. This is given a 0 volt, 0 value. So the boundary conditions, we'll quickly go and so temperature being a update, and expand this, go to initial T. We will give an internal field 3 absolute 0 condition, and we will set the dimension of the 4th to 1, being the 4th quantity holding the temperature. So we will add boundary values, introduce the first boundary value, it's patch 1, which was the connecting pipes, an insulating boundary condition or 0 gradient. That being patch 2. In this to patch 3, give this again a fixed value. to be the temperature at the riser side. So what is the temperature which I had given? 350 Kelvin. So I will be adding 350 and the patches. So we click on update. So once your initial T is updated, you and all your pre-processing. So we will move on to solver. Is once that is recognized by our platform. So we will use and open the solver. So here you're seeing that the solver has been initiated and you are currently converting the UNV file to foam, which in a short while we will get a completed result. So what it has done is taken using the standard SI units, all the points within the cell has identified the cells, and also identified the patches which we give. And we had named the patches as patch 1, patch 2, patch 3. So all the patch 1, patch 2, and patch 3, these values are basically the number of elements which it has identified within the mesh. After that is done, we initialize the initial. We click on solve. Conditions have been initialized. Now we run the Laplacian form or the Laplacian solver. So while this runs, we will quickly go back and a little more into what the types or methods of solving within the solver. So we have used the simple solver and we have used a preconditioner as PCG, and it is basically using DIC PCG. This is beyond the scope of our understanding at the moment. So you just have to understand that it is using a preconditioned method where it the fluctuations between successive iterations are controlled. It's solving one, as I mentioned earlier, method, and it starts and the final residual. So what this does is, after solving the first time, it reiterates twice because it gave the number of ended non-orthogonal correction factor as so it has calculated from point. now, values which we have calculated. So it's correct. The process while quickly look at conclusions come will better. Followed is that for flux your calculation is always normal to the element. One not be able to calculate between happening. It's only diffusion. So the basic answer is that you can either use a hex or a tetra mesh, but you may have, because if it's a larger size, you will not be able to. In order to be able of the temperature is being if you look at the mesh element type, it shouldn't matter. The post processor loaded, and this is our model. So you can move the model around within the browser itself and position it. So we open the inspector panel, open representation under, like, change the palette, probably put blue to red. Will show you how the I will that the temperatures it is showing is what the temperature of 900 Kelvin in patch. probably to we should concentration in hand each of these time steps. It's an and 900 Kelvin. To account the highest temperature and the lowest temperature and the radiation. To do is we will so there is really these time steps building up, and by the time solution, seeing the residual, the solver log, where you have seen that towards the end, successive iterations are the steady state results which we saw. We can understand that and when to use what kind of a boundary condition. Dirichlet is used when you are giving absolute values, like we did for patch 2 and patch 3. And Neumann boundary condition, Neumann boundary condition was given at patch 1, Dirichlet was given at patch 2 and 3. And the difference between a steady state and the transient heat conduction, where the transient heat conduction happens at each time step of physical time and not the simulation time. And in the steady state, we'll only be matching the time for the simulation to occur. So thank you for participating, and I would definitely like to express my thanks to all the viewers over here. And we shall come back again with more simulations of how different kind of analysis can be done on the learning platform. Thank you.